Applications of recurrence relations. Recall that a recursive definition of a sequence specifies one or more initial terms and a rule for determining subsequent terms from those that precede them. Also recall that a rule of the latter sort is called a recurrence relation, and that a sequence is called a solution of that recurrence relation if its terms satisfy the recurrence relation. Example 1. Consider this problem originally posed by Leonardo Pisano, also known as Fibonacci, in 13th century in his book Liber Abaci. A newly born breeding pairs of rabbits is placed on an island at the beginning of month 1. Each breeding pair mates at the age of 1 month, and at the end of their second month they always produce another pair of rabbits. Suppose that rabbits never die but continue breeding forever. Find the recurrence relation for the number of pairs of rabbits on the island after n months. Solution: denote by f sub n the number of pairs of rabbits at the beginning of the nth month. We will show that f sub n for n equals 1, 2, 3, and so on are the terms of the Fibonacci sequence which we defined before. N denotes the month. A sub n denotes the number of newly born pairs in the beginning of month n. B sub n denotes the number of reproducing pairs in the beginning of month n. And F sub n denotes the total number of pairs in the beginning of month n. In the beginning of month 1, we have 1 newborn pair and 0 reproducing pairs. The total number of pairs is 1. In the beginning of next month, the newly born pair becomes a breeding pair. They are not newly born pairs, because in the previous month we don't have reproducing pair, and the total number of pairs is 1 again, the sum of these two. At the end of month 3, we have 1 newborn pair, because in the previous month we have 1 reproducing pair. The number of reproducing pairs is 1, because in the previous month we don't have newly born pair. And the total number of pairs is 2. Month 4. In the previous month we have 1 reproducing pair, so we will have 1 newborn pair in the next month. In the previous month we have 1 newly born pair, it becomes breeding pair, and this breeding pair remains breeding. So 1 plus 1 is 2 reproducing pairs. The total number of pairs is 3. And we fill out the next 2 rows similarly. So in general, for n greater than or equal to 1, f sub n is a sub n plus b sub n, according to our definitions. For n greater than or equal to 2, a sub n is b sub n minus 1. Yeah, the newly born pairs at the end, in the beginning of month n, equal to the number of reproducing pairs in the previous month. And b sub n is b sub n minus 1 plus a sub n minus 1, because the newly born pairs from the previous month become reproducing pairs, and the reproducing pairs from the previous month stay reproducing in the next month. Hence, b sub n is equal to b sub n minus 1. Here we can replace a sub n minus 1 with b sub n minus 2, according to this. So this equality can be replaced with this one for n greater than or equal to 3. So for n greater than or equal to 3, we also have a sub n equals a sub n minus 1 plus a sub n minus 2, because you see these equalities. Thus, f sub n, which is a sub n plus b sub n, is this. A sub n minus 1 plus b sub n minus 1 is f sub n minus 1, and a sub n minus 2 plus a sub n minus 1 is f sub n minus 2. So, the sequence with n term f sub n satisfies this recurrence relation for n greater than or equal to 3, together with the initial conditions f1 equal 1, f2 equals 1. Because this recurrence relation and the initial conditions uniquely determine this sequence, the number of pairs of rabbits on the island after n months is given by the nth Fibonacci number. The Tower of Hanoi, a popular puzzle called the Tower of Hanoi, consists of 3 packs mounted on a board together with discs of different sizes. Initially, these discs are placed on the first pack in order of size, with the largest on the bottom, as shown on this figure 2. The rules of the puzzle allow discs to be moved one at a time from one pack to another pack, as long as the disc is never placed on top of a smaller disc. The goal of the puzzle is to have all the discs on the second pack in order of size, with the largest on the bottom. Let h sub n denotes the number of moves needed to solve the Tower of Hanoi problem with n discs. Set up a recurrence relation for the sequence h sub n. We begin with n discs on pack 1. We can transfer the top n-1 disks following the rules of the puzzle on peg 3 using h sub n-1 moves. We keep the largest disk fixed during these moves. Then we use one move to transfer the largest disk to the second peg. We can transfer n-1 disks from peg 3 to peg 2 using h sub n-1 additional moves, placing them on top of the largest disk, which always stays fixed on the bottom of peg 2. Moreover, it is easy to see that the puzzle cannot be solved using few steps. This shows that h sub n is equal to 2 times h sub n minus 1 plus 1. The initial condition is h1 equals 1 because one disk can be transferred from peg 1 to peg 2 according to the rules of the puzzle in one move. Figure 3 gives an illustration of the position after the first h sub n-1 moves. We can use an iterative approach to solve this recurrence relation. Now that h sub n is 2 times h sub n-1 plus 1, then replace h sub n-1 with 2 times h sub n-2 plus 1. Use the distributive law here to write the sum this way. Then replace h sub n-2 with 2 times h sub n-3 plus 1. Distributive law applies, and we rearrange the sum this way. Here 2 to the 2 cubed h with index n-3, and then consecutive decreasing powers of 2 added. Continuing this way, we'll get 2 to the n-1, h1. The sum of the indexes here and here is n, so n-1 plus 1 is also n. And then add the consecutive powers of 2 starting from n-1 ending to 0. But h1 is 1, so we get this sum, which is the sum of geometric progression, and it is equal to 2 to the n-1. Example 3. Find the recurrence relation and give initial conditions for the number of bit strings of length n that do not have 2 consecutive zeros. How many such bit strings are there of length 5? Solution. Let a sub n denote the number of bit strings of length n that do not have 2 consecutive zeros. To obtain a recurrence relation for the sequence, know that by the sum rule, the number of bit strings of length n that do not have 2 consecutive zeros equals the number of such strings ending with a 0 plus the number of such strings ending with a 1. We'll assume that n is at least 3, so that bit strings has at least 3 bits. The bit strings of length n ending with 1 and do not have 2 consecutive zeros are precisely the bit strings of length n-1 with no 2 consecutive zeros and 1 added at the end. Consequently, there are a sub n-1 such bit strings. Bit strings of length n ending with a 0 that do not have two consecutive zeros must have 1 as their n-minus first bit, otherwise they would have two consecutive zeros at the end. It follows that the bit strings of length n ending with 0 that have no two consecutive zeros are precisely the bit strings of length n-2 with no two consecutive zeros, with 1 0 added at the end. Consequently, there are a sub n-2 such bit strings. We conclude that a sub n is equal to a sub n-1 plus a sub n-2 for n greater than or equal to 3. The initial conditions are a1 equals 2 because both bit strings of length 1 satisfy the requirements of the problem. And a sub 2 is 3 because of the 4 bit strings of length 2, only these 3 do not have two consecutive zeros. To obtain a5, we use the recurrence relation 3 times. For a3, we get this. A2 is 3, a1 is 2, so a3 is 5. a4 is the sum of the previous two terms, and we know them, 5 and 3, so a4 is 8. And a5 is the sum of a4 and a3, and we know a4 is 8, a3 is 5, so a5 is 15. The next is a problem for you to solve. Find the recurrence relation for the number of ways to lay out a walkway with slate tiles of the tiles, if the tiles are red, green or gray, so that no two red tiles are adjacent and tiles of the same color are considered indistinguishable. B. What are the initial conditions for the recurrence relation in part A? How many ways are there to lay out a path of 7 tiles as described in part A? Hints for part A. Consider two cases for n greater than or equal to 3. The first, the last tile is green or gray. Actually, here we have two subcases, last tile green, last tile gray. In second case, again, consider here the case when the last tile is red. The next to the last tile cannot be red, so it is either green or gray. And here we again have two subcases. The answers are presented here for A, B, and C. Try to get those answers.